All right. So it's 1 o'clock. Thank you all for joining for the senior design, chemical engineering senior design presentations. These students have been working hard for the past 2 quarters, the winter and spring quarter, on developing a hydrocracker. And they'll be presenting their work on that optimization. I think we'll hold off questions till the end, so it'll be about 15 to 17 minutes for presentation. And then for any questions, you can put those in the chat, or we can unmute at the end if you have any questions for the group. So with that, why don't we get started? And Elizabeth, if you want to take it away.
Alrighty. My name is Erin Gahagan.
I'm Adam Ramachandran.
I'm Casey Stringer.
I'm Elizabeth Talbot. And for this design project, we were asked to design a catalytic hydrocracker system. So we will begin with an overview of the system. This is our process flow diagram. In the next few slides, I will go into more detail of different aspects of the system. But for the overall process, we have our reactor and then 3 towers following to separate out all of the products. So to begin, we have a hydrogen and VGO feed, which are both fed to our reactor. From there, they're passed through a heat exchanger to be cooled, and then into a flash drum. The flash drum separates out the hydrogen from the rest of the components, and the hydrogen, as you can see, is recycled back to the hydrogen feed stream. So for our reactor, it has a volume of about 98,000 cubic feet. It's run at a pressure of 2,176 psia, a temperature of 842 degrees Fahrenheit, and a space time of about half an hour. So the bottom stream of the flash drum is then fed into our first tower. This tower has 40 trays with a feed on tray 8. And as you can see, it separates out our VGO at the bottom. And instead of using a reboiler on this tower, we used a furnace because of the high temperature of the VGO. So the top stream is then fed to the next tower. This tower has 18 trays with a feed on tray 6, and it separates out the diesel. Finally, on our third tower, the kerosene is separated out the bottom, and the naphtha and LPG at the top. This tower has 25 trays with a feed on tray 12.
So before we could run any actual simulations on this process, we had to make sure that some assumptions were correct and valid. So the first of those we had to deal with was justifying thermodynamics. We found a literature article that gave us the vapor-liquid equilibrium of some hydrocarbons and hydrogen. And it also gave us a breakdown of the feed that they used to determine that data. So we modeled a feed in ChemCAD as similar to that in literature as possible. And we ended up having to make some assumptions on the residue fraction so that the simulation feed wouldn't boil off at any of the conditions we had to test. Once we had done that, we ran this simulation feed through a flash drum at these temperatures and pressures and compared it to the literature data for mass fraction of hydrogen in both phases, as well as the partition coefficient K value. We ran 8 different thermodynamic models, and only 4 of those 8 had valid K values as well as mass fractions in both phases. So if we take a look at the graphs here on this next slide, we can see the results of the K values on these models. We ended up seeing that PSRK and Grayson-Street, GS here, were the best models, as these were closest to the literature K values. And we chose Grayson-Street due to its higher accuracy at the higher temperatures, as you can see in the graph for 808 degrees Fahrenheit.
Next, we had to decide how many components we needed in our system. We did this by running a distillation column with different combinations of cut fraction component. And this table shows the feed rates for each cut fraction. We then graphed these to determine the minimum number of components for each cut fraction. So for our LPG and naphtha, we determined that we needed 3 LPG components and 2 naphtha components. Between naphtha and kerosene, we determined 4 naphtha and 5 kerosene components were needed. Kerosene and diesel, we needed 3 kerosene and 5 diesel components. And then for diesel and VGO, we decided on 5 diesel and 6 VGO components. So from these numbers, we chose the highest ones and determined that we needed a total of at least 23 components.
So once we had determined the amount of components that we needed, we had to determine the identities of those components. So we pulled straight chain hydrocarbons and a few alkyl benzenes from ChemCAD and compared their boiling point ranges to those of the cut fractions. And then we tried to distribute those as evenly through the cut fraction as we could. You can see here that we have the resulting components for each cut fraction, as well as hydrogen included in the simulation. So once we had those reactants and compounds, we developed a reaction scheme. So you can see that these first 8 reactions are the hydrocracking of the VGO, and then the remaining reactions are to represent the further decomposition of VGO as it spends more time in the reactor. So once we had these reactions, we had to develop kinetic parameters to fit the literature data with our ChemCAD results. We did this at different spacetimes. And at lower spacetimes, we were able to get a very good fit. But as the spacetime increased, it became more difficult to match. You can see here, starting at 1 hour spacetime, the VGO in the simulation starts to deviate from literature behavior. And in 2 hours, it is very different. So the error introduced by this strange behavior in the VGO is what trickled down into our other cut fractions, and that error just propagated. But overall, we had fairly good kinetic fits.
Alrighty. So to cost out our reactor, it is at high pressure and volume. We use a slightly different equation than what we normally would have used. This equation is focused primarily on volume. So as your volume of your reactor increases, and then therefore your space-time will increase, the cost is going to increase as well. For our almost 100,000 cubic feet reactor, we have a CP value of about $80.8 million, but the bare module cost with that application of the pressure factor brings the cost up to almost $329 million. We costed out our compressors using the actual power given by the ChemCAD components, and our fresh hydrogen feed, that bare module cost is about $8.9 million. For our recycle hydrogen feed, it's about $12.1 million. And the reason for a much larger cost for our recycle compressor is because it has a much larger differential pressure than our fresh hydrogen feed, and therefore it's going to need a much larger power. Our FCI impacts. Our reactor composes of about 70% of our FCI, and then followed by almost 20% for our 3 towers and their respective trays. And then our next most expensive would be our 2 compressors, followed by our pumps, and then our exchangers, and with the vessels and furnace, with small percentages impacting on the FCI. Our total FCI is about $556 million.
So because our raw materials and products are considered to be commodities, we needed to determine an accurate cost for pricing these out in order, as one of our main major aspects of our costing analysis. And so for the VGO, we used data published by the EIA, though there were some years that were omitted in their publication. And because of this, we decided to take the average deviation of the reported years, which resulted in a value of 64 cents per gallon. And then for diesel, there were much more data provided, even though it's also provided by the EIA, but we decided to take the 5-year average over the last 5 years, and which returned a value of about $1.92 per gallon. And then for similarly for kerosene, we also took the 5-year average, which returned a value of $1.86 per gallon. And then for naphtha, this data was not found by the EIA, but by the Trading Economics. But we also took the 5-year average, giving us a value of about 26 cents per pound. And then for our LPG, we once again took the 5-year average, and this resulted in a value of about 73 cents per gallon. And then for our hydrogen, we crossed it out as though we were using a steam methane reformer, and that resulted in a value of about 42 cents per pound. And so this affects our NPV by, well, it gives us a best case NPV is about $1.2 billion, with 51% of it being revenue, about 25% being from the equipment itself, and then 22% being from the raw materials.
Alrighty, so for our reactor optimizations, we varied the resonance time and as well as the temperature. And as you can see in this graph, at around a half an hour residence time is where most of these curves are peaking, and our highest NPV peak is at a temperature of 842 degrees Fahrenheit. And we also wanted to compare what the conversions of the VGO was at those same points. And as you can see, the third point is generally where they're starting to peak, and the third point corresponds to half an hour space-time as well. And again, it shows the highest conversion occurs at the 842 degree Fahrenheit and half hour space-time. And this shows this is just to compare our model that the literature values at that point at 842 degrees Fahrenheit and half an hour space-time. The naphtha, kerosene, and diesel are almost exactly the same, with some slight variations with the LPG and the VGO. And so at this point in time, our model is fairly accurate.
So we also decided to optimize our towers, and for the first tower, the feed tray location was optimized in a 40 tray tower to be fed in at tray 8. The second tower was optimized for both the number of trays and the feed tray location, and it was determined that we would need 18 trays and the feed tray at 6. And then for the third tower, once again, the feed tray location and the total number of trays was optimized. And for this tower, we have 25 trays and the feed tray at 13. However, as you could see with all 3 towers, the feed tray location and the number of trays does not have that much of an effect on the NPV. So it didn't really matter what we actually chose, because it wouldn't have had too much of an effect. But we also decided to optimize the condenser on the third tower by changing the fraction recovery setting for the condenser. And so by doing that, in order to determine how pure of a stream we can get that's still cost effective, and this resulted in a value of 0.998 fraction recovery.
The safety considerations to take into account is that the reactor is operating at very high pressure and temperatures, and the reactions occurring are exothermic. And so there will be pressure release valves in place in case of a runaway reaction, as well as a bypass system to stop the flow into the reactor as it approaches runaway reaction conditions. We're using refrigerant on some of our condensers in the top of the 3 towers, and so those will require safety relief valves on both sides of the utility fluids, and we'll have relief valves placed on all major equipment and lines to ensure pressure relief in case of overpressuring. We will have a sensor with alarms for the reactor, both with pressure and temperature. Our flash drum will just have a pressure sensor. And on the reflux drum, we'll have a level, on the reflux drums, we will have a level sensor, and then we'll have a pressure sensor with an alarm on there just in case the condenser does not fully condense and we have an increase of pressure. And we'll have temperature sensors on the top and bottoms of our 3 towers.
Some environmental aspects that should be taken into consideration are to not have any leaks or spills in order to prevent any type of contamination of the ground and water sources that could then potentially cause harm for both people and wildlife. And having a good maintenance schedule and safety culture will help prevent these leaks and spills, but we also need to make sure that the plant maintains compliance with all federal, state, and local regulations. And then assuming that our facility will be built in Louisiana, the amount of greenhouse gases that are emitted should fall within these ranges of the Louisiana petroleum refineries. The average Louisiana petroleum refinery or facility releases almost 2 million tons of greenhouse gases a year. So as long as we fall within this range, our plant should meet these regulations.
So throughout our design process, we considered a few different topologies for our system. Before narrowing our system down to a 3-column system, we had a 4-column system. We also considered one with 2 flash drums, but it turned out to be uneconomical. We considered a system with a fractionator, but we had issues converging that in KimCAT. And then we also considered a system with 2 reactors in parallel. Are there any questions?
As a reminder on questions, you can either send me a note in chat and I can unmute you, or if you want to raise your hand, I can unmute you so you can ask a question. Rachel.
Can you hear me now? Back on your optimizations, your temperature with your residence time was 842, but it looked like that was as high as you went. Did y'all check higher temperatures?
We had in the past, but not necessarily with graphing it. And that was the extent of our literature data was at 842. And so through validity within our model, we couldn't necessarily exceed that.
Thank you.
And I guess I had kind of a speculation question on your part. I thought it was interesting how you looked at the cost of the different commodities, and over time, they kind of fluctuate. If you could speculate, I imagine would you expect a correlation between those? If the price of one commodity goes up, would another one go down? Or do you think there's any relationship between what you're selling your kerosene, diesel, or the different commodities for?
Well, there's definitely a correlation between them. We've seen that like over time they tend to follow each other, but there's also cases where one will fluctuate a lot and others won't necessarily follow that fluctuation.
And it's gonna be like positive, or if one goes up, they all kind of follow that same track, or are they negative, where the price of one goes up, the other one goes down?
Mm-hmm. Yeah, they generally follow the same trend.
All right. Well, if there are other questions, I would say let's thank our speakers. I guess everyone in the video wants to do a little clap. We can we can thank our speakers that way. So thank you so much, Aaron, Adam, Elizabeth, and Casey. All
Thank
right.
you.
So we'll give a few seconds to switch over to the next group. So hold on a second. Yeah. So Riddick. Sierra. And Sierra, Ashley, and Holden, I believe you're all unmuted.
Good here.
All right, take it away.
All right, are we ready? Hi, my name is Sierra Matthews.
Hi, my name is Ashley Riddick.
And my name's Holden Zuger, and thank you for coming to our capstone presentation on our catalytic hydrocracker system.
So here is an overview of our system. We have fresh hydrogen coming in along with fresh VGO. Our reactor is operating at 753 degrees Fahrenheit and a pressure of around 2300 psia. And so after the hydrogen and VGO are reacted, the product stream goes into a flash drum that further separates out the hydrogen to recycle. And then the bottom product goes into a series of 4 columns to separate out the various cuts, the diesel, kerosene, naphtha, and gas. And then the VGO is also recycled. Here's an overall mass balance to keep track of what products are going where. Our VGO is going in with the hydrogen with a hydrogen to hydrocarbon ratio of 35 moles. And you can see right here that the stream 10 diesel has the highest mass flow rate at 382 pounds per hour, and that's also our most profitable cut. Here is an overall energy balance. So this is just showing that we have more energy being consumed than produced. And so the likelihood of us experiencing thermal runaway within our reactor is low.
So here we can see a main overview of the total system. I'd like to point out a few things. Our reactor is split into 4 equal in volume, and the flow rate is also split equally 4 ways, and this is to ensure that our kinetics stays consistent from 1 large reactor to 4 smaller ones. We did this to more accurately represent the price, because the equations and the graphs that we used for our pricing equations did not extrapolate to the total size of 1 reactor, so instead we split it into 4. We do have 2 recycles, and we have 2 control loops on each recycle. Again, like Sierra said, we have a flow control to keep that ratio of hydrogen to hydrocarbon consistent, and then we also have a temperature control loop on our reactors to control any thermal runaway. And also this, the temperature is coming from our diesel stream on that second column, and this is just a way to go and preheat our feed stream for our VGO in order to cut some utility costs on that first fired heater.
Our overall best NPV was 1.03 billion. The reactor was about 93% of our total cost, followed by 3% from the towers. And our revenue, as mentioned earlier, mostly comes from diesel, which takes up about 63%, while kerosene follows closely behind, or follows behind at 17%. Overall, for our general equipment, as mentioned before, we have 4 reactors. So in summation, these 4 reactors cost about $500 million. Now, 70 million of that does come from the catalyst that we are costing as well. The next most expensive vessel is our flash drum vessel, which is made of the same material as the reactor. Both are costed as nickel alloy in order to avoid hydrogen embrittlement. And this one is also, this flash drum tends to be very expensive, mostly because it is also separating out the rest of the hydrogen that we're sending back into the reactor. For our 4 towers, the most expensive one is our tower 2 that is separating out our diesel. Diesel, as mentioned earlier, is our highest created product, so it does have the highest flow rate, which is what leads to why our tower 2 is so expensive. For our utility equipment, our most expensive pump is our first one for the feed. This is what's sending in the feed to the reactor itself, so it is the highest flow rate that we're experiencing. Below that, we have the compressors. So both of the compressors are expensive. They're about 1.5 to 1.9 million. I'll explain the actual costing of that later, but it is expensive mostly because of the fact that these are also made out of nickel alloy as the reactor to avoid the hydrogen embrittlement, as mentioned before. We have 3 fired heaters, the most expensive one being the fired heater on our first tower. This tower is the one that separates out our VGO. We also have a fired heater for the tower that separates out diesel and for our pre-feed, as mentioned earlier by Holden. The rest of our heat exchangers, the most expensive ones are our condensers on our 3rd and 4th tower. So these are the towers that are separating out kerosene and then naphtha gas. These condensers are so expensive because they're at very low temperatures. For the sizing equations, we have the compressor. This is how we're sizing the horsepower in order to see how much they would cost. We are assuming that both compressors are running at about 80% efficiency and that we have to get the hydrogen from about atmosphere, either from where it's coming from as a feed or out of the flash drum, to 2000 PSI, which is the pressure of the reactor itself. Our catalyst is a tungsten trioxide base, which takes up about 30%, and it has an aluminum oxide and silicon oxide support, which takes up about 70%. This catalyst is based on our literature, so in order for us to use our kinetics, so we did cost them as the literature said that they were made. So we're assuming it takes up about 2/3 of the volume of the reactor, so we're accounting for it as a one-time cost with the cost of the reactor itself at about $70 million. These are reactor optimizations. So as you can see, we have a peak at about half an hour residence time. We attribute this to the fact that low residence time aren't making enough product in order to be profitable. However, higher residence times, because the reactor is so expensive, that it is extremely the cost of the reactor overpowers the revenue we're making from product. So we're mostly profitable as shown in the NPV versus temperature graph at a residence time of 0.5. And we tend to be at the highest NPV whenever we're running around 753 degrees Fahrenheit.
So for our tower optimizations, instead of doing the amount of trays within the tower, because we had incredible issues with that, we decided to go to a more a different route, and we optimize the pressure within each tower. So on the left side, we can see that our MPV is maxed out around $25 million, and this is at around 175 PSIA. I do want to note that this is for all 3 towers being consistent or constant. So as we change one tower pressure, the other tower pressures change the same amount. We do see a unusual jump in utilities around 125 PSIA, and we contribute this to our first distillation column because, which we will talk about later, is going to be under pressure. And so as we or under a vacuum, as we increase the pressure, the utilities cost for that tower specifically skyrocketed. And on the right side, this is more the tower cost individual versus tower pressure. And I wanted to point out that Unit 4 is our largest tower with the diesel separation in it. And that is what we are assuming is making the tower CBM so large. So here, this is our methodology of increasing or optimizing the tower pressures. We started with the first tower, and the first tower, as you can see on the left, it reached a maximum at around 5 PSIA. We were unable to go any lower than that because of KimCAD itself breaking. So 5 PSIA was our optimum for Tower 3 at about $1 billion. And from there, we set Tower 3 at 5 psia and then worked on each tower ladder. And so the next tower we optimized from 5 psia up to wherever the maximum was, and we noticed that it did plateau around 155 psia. And so once Tower 3 and Tower 4 was set, we went to Tower 5, did the same thing, Tower 6. So we kept that methodology consistent, and we ended up with all 3 towers having a maximum or an optimum at 155 psia.
In our system, we did find that there was an ability to have heat integration. Our diesel tower, as discussed earlier, is our biggest tower. It's also our hottest tower because it's at a much higher pressure than the rest of our towers, or it's at a higher pressure and a higher flow rate. So the reboiler line is actually at about 985 degrees Fahrenheit. So we decided to use that in order to replace the preheater or the fire heater for the feed VGO. We are heating up the feed VGO by about 200 degrees, from 500 degrees to about 700 degrees for the feed into the reactor itself. And in doing so, we are actually able to reduce the diesel temperature from about 900 degrees to 700 degrees, making it much more safer. Now, in doing so, we're actually saving about $70,000 in utilities. We're saving about $500,000 in the actual FCI, and the overall MPV from using this heat integration is about $1 million. We have a sensitivity analysis as well for our raw materials and our products. So the base case line that we have is our NPV at about $1 billion. That's the dotted line in the middle. And we costed this NPV using an average of the raw material and product costs from 2016 and 2019. As you can see, if we would have used the individual months data, we could have had a peak in April 2008 at about $7 million. Yeah, $7 billion, while we could have had a negative peak in June of 2016 of about negative 2 billion. Our NPV does ride relatively in the middle over this entire timeline, so that we do tend to see that as being justified of using the average pricing that we did.
So we tested 6 different thermodynamic models to see which would model our system most correctly, and we used a decision matrix to help make this decision. And so we gave a numeric score to each of the thermo models based on the categories on the left. And so we looked at the sum of squared error of the paraffins, naphthenes, and aromatics. And we did find that we had the same score for Unifac, NRTL, and Uniquac. NRTL is for 2 liquids, so that wasn't applicable for our system because we have a mixed phase. And Uniquac just gave us more consistent calculations, and so we just went ahead and pushed forward with Uniquac. It did model our system pretty well, so here's an example of our literature data compared to the data that we had from our ChemCAD simulation, and so it matches pretty closely for the paraffin vapor group. We also did it for the liquid phase, and we did it for the naphthenes and the aromatics and paraffins as well.
So for our component database, this is the slide that I'll be going over our VGO or our feed. We wanted to focus on the carbon number because this heavily impacts our molecular weight, which we wanted to match with our literature. We also looked at the structure, whether it was a straight chain carbon, a cycloparaffin, or even an aromatic with some double bonds. We looked at the boiling point, and that's, as you can see on the graph, the VGO literature versus simulation. This is from our different boiling points because of the different standards that are run in order to have the VGO be, in order for the VGO to be more as the literature. And so the feed composition, as you can see on our right, is made up of 4 components at those specific ratios. We did the same thing for our feed. We wanted to make sure our boiling points were in the correct cut fractions that we were going to be separating in. And of course, we looked also at the carbon numbers and the structure in order to make sure that when it did separate, it separated into something that related to our cut fraction physical properties. So here you can see our reactor model kinetics. We use the Arrhenius equation by changing the frequency factor and activation energy. There's a lot going on this overview, so just to show what is going on, we have multiple colors representing different cut fractions. We have different lines and dashes. These represent different temperatures of our simulation data. And finally, we have shapes, and these shapes, the different shapes indicate different temperatures, and they also indicate the literature data that we were regressing towards. So this is more specifically looking at 3 temperatures. We were able to match very nicely, especially in our upper temperatures. We were able to get a maximum with our diesel at around 1 hour of a residence time. And as we increased the temperature, we did increase the amount of inaccuracy or accuracy with the literature to our simulation. And as you can see on the next slide, the accuracy is represented with our sum of squared errors method. And since we found an optimum to be near the higher temperatures, we wanted our accuracy to be consistent between those. So we did lose some accuracy in the lower temperatures, but we deemed that this was necessary in order to be more accurate to the literature in our higher temperatures.
To start off with our safety calculations, we have our energy generated versus removed at the reactor. So the energy generated here is indicated by the red line. This is taken from ChemCat as the Q of the reactor itself, the million BTU per hour that's generated from the reaction at that run at that temperature, while the RT represents what is being removed. So we are assuming we have a jacketed reactor where we have cooling water used in order to cool it down. All extra energy we're assuming is going into turning this cooling water into steam. This steam can be used as a utility upstream or downstream somewhere else in the plant. So we did a mass or a balance at 753, the temperature our reactor runs at, in order to find out how much mass of water we should be sending in usually, which we discovered to be about 287,000 pounds per hour. Now, assuming that we don't change this amount of water, we plotted that against what it would be if the temperature of the reactor continued to increase. So what we discovered here is that we are relatively stable from around 745 degrees Fahrenheit to about 775. But then at around 800 degrees Fahrenheit, there's a major jump in the energy generated by the reactor. And not only does it go over what we expect to be able to remove, but it continues to increase at the same rate, meaning that we are in danger of being in a situation where we could have a runaway reaction at this point. So were we to get that high, we would either need to increase the amount of water or find some other way to reduce the temperature of the reactor.
Some more safety calculations were done looking at various streams and their cuts. And so this is calculating the equivalent mass of TNT. And so you can see that the largest mass equivalent TNT is for the crude oil cut, and that's largely due to the higher flow rate of the crude oil stream. We were further able to look into what would actually happen if this equivalent mass of TNT were to go off. And so this is damage within around a football field radius. And so you can see that we have the largest danger with the crude oil. And again, that's because of its large mass flow rate. And then we also would see resulting minor damage in structures or small and large windows as well. And so that's all we have for our presentation. Do you guys have any questions?
You can send a message in chat that you have a question, or feel free to raise your hand in the participant window. Any for questions? All right. Well, if there are no questions, let's kind of give thank our speakers with a visual round of applause. So thank you so much, Sierra, Ashley, and Holden.
Thank you.
Thanks.
All right. Oh, and Aaron, did you give them a high five or? All right, so give a few seconds and we'll switch over to Clayton and Austin for their presentation at 1:40. So hold on for a few seconds while we make the switch.
All right. Get Austin unmuted.
Can you hear me?
Yeah. All right. Hello, everyone. My name is Clayton Carrick.
Hello, my name is Austin Wills, and this is our VGO catalytic hydrocracker presentation. I will start us off by going through our presentation overview. First, Clayton will talk about our systems topology. Then we'll go over our reaction overview, which will include the thermodynamic and kinetics validation. Then we will speak about the more important pieces of our equipment sizing and costing methods. Then I will get into our systems optimizations that we've made. Following that, we'll talk about the process safety aspects of our project. And lastly, we'll talk about some environmental considerations that we've made.
All right, so to start off, like Austin said, I'll cover our topology. This is an overview of our entire systems topology. As you can see to the left, we start off with our fresh VGO and hydrogen feed, which are fed at, the hydrogen feeds into a compressor, which compresses it to the operating pressure of upwards of 2000 PSI. It then goes into a preheater, which recycles some of the heat that the reactor produces before going into a fired furnace to heat it up to the reaction temperature of around 800 degrees Fahrenheit. After the reactor goes into a flash, we do have a hydrogen and VGO recycle, which is controlled. Those flows are controlled by a controller, which this is to maintain a hydrogen to hydrocarbon feed ratio, which is very important for our reaction kinetics. So after the flash drum, the liquid product goes into an expander to expand its pressure, or to reduce the pressure before going into a distillation column, which will separate our gas, naphtha, kerosene cuts from the diesel and VGO cuts. These two groups move forward to secondary distillation columns to be separated further. One important note that I'll speak on more later on in the presentation is that a couple of these towers are driven by fired heater furnaces instead of heat exchangers. I'll discuss later.
From here, you can see the mass flow rates of our reactor section of our topology that Clayton just described. Blue signifying mass flow rates feeding into the system, green representing recycled streams, and red leaving this portion of the system. So the red will go into our separation processes.
Too much.
Now we're moving into the distillation section of our system. This section is labeled similar to the last, with blue signifying the feed coming in, green recycling, and red leaving as our products that will be sold. On the right, you can see the mass of each of our products leaving our system per hour in pounds. And you have around 30,000 pounds of gas, around 43,000 pounds of naphtha, 55,000 pounds of kerosene, and 122,000 pounds of diesel, which is our largest profit margin product. And then we have around 400,000 pounds of VGO being recycled back into our reactor system.
Next, we'll kind of go over the science behind all of it, which would be the reaction, kinetics, and thermodynamics review. So to start off, we needed to ensure that we were modeling the interactions between the hydrogen and VGO correctly. So to do this, we found literature data which described how much VGO was going to be vaporized as temperature increased. And so this chart depicts that line as well as the lines produced through KimCAD simulation under different equations of state. And from this chart, you can see that our best fit, our closest fit would be VTPR equation of state, which we did not move forward with through the rest of the project because this equation of state increased our computation time to a point where it's just kind of unforeseeable to perform the optimizations that this project required. So we move forward with our second closest fit, which would be King Robinson, the yellow line there. Next, we wanted to make sure that we were, well, we have all these different cuts, VGO, diesel, kerosene, naphtha, and gas, which are understood air boiling point ranges, which we decided there to the left. You can see the boiling point range that we decided. But to the right, we have our full component list that we chose to actually model these component cuts. And you can see in this chart that we have about 4 components per cut, which accurately models each of those cuts. We have about 4 because we put we progressively put components into a distillation column and plotted the duty of that distillation column until it plateaued. And through that process, we found about 4 components was an accurate representation of each cut. So after this, we wanted to accurately model VGO, vacuum gas oil, into the hydrocracker, or accurately model the composition of that feed. So as you can see from our literature data, we have about 1/4 of that feed is aromatics and 3/4 of it is non-aromatics. So from this, we created our reaction network, which takes each of those 4 VGO components that we chose in the last step and degrades them through the kinetic model shown in the middle there. And the full network is listed to the right. To represent and to ensure that the system was accurately simulating the interactions or the kinetics, we plotted product distribution against literature data found for 716, 752, 788, and 824 degrees Fahrenheit at different resonance times. And these are those graphs. One particular note is that at 824 degrees Fahrenheit in literature, the diesel product distribution decreases as resonance time increases, or there's a degradation there. So we were able to accurately simulate that character of the graph.
Next, we'll go into our commodity pricing and how that was done. So the graph below is the yearly average prices for VGO, diesel, and kerosene in dollars per gallon over the years of 2000 and 2019. 2020 was not included due to the significant price drop from our current circumstances with COVID-19. These prices were pulled from EIA.gov and graphed to demonstrate how accurate their average is. Naphtha, to the bottom right, was not on EIA.gov, so we had to do further research to locate its prices over the past couple of years. We were able to find them on businessinsider.com, and we took the average price from 2005 to 2019, which you can see in the graph below. On the next slide, you will see the yearly average of liquid petroleum gas, which over the years of 1978 to 2019, and this average was taken further back due to the understanding that gases should be less desired product in our system. Below the graph, you can see the flow rates of each commodity entering and leaving our system with their prices per gallon and the total net value of the system running for a year. Due to the large amount of hydrogen that is required for our system, we will take advantage of the steam methane reforming unit on site. This unit uses methane and high temperature steam over a nickel and platinum catalyst bed to create hydrogen and CO2. CO2 will be scrubbed before leaving the system to decrease the environmental impact. Based off an article I found in 2008, this process costed about $2.27 per kilogram, with the methane cost of $10 per million BTUs. Our goal was to determine how much the hydrogen costs came from the methane pricing. So we analyzed the methane price similar to our other commodities and found the average of $4.95 per million BTUs over a 20-year span. Based off the article, the methane price consisted of 60% of the cost of the hydrogen, so we maintained the previous FCI cost and reevaluated the methane portion of the cost to get a new hydrogen price of $1.74 per kilogram, like the equation demonstrates above.
Next, we'll kind of get into our equipment sizing and the costing based off of that sizing. So just to kind of get an idea of the contribution of each equipment to our total FCI or total equipment cost, this is a pie chart representing that. As you can see, the reactor is the biggest portion of that cost. which is to be expected because it's a large vessel and it also is the most important vessel of our system. So that was costed based off the equation below, which is based off of the volume of the reactor. And it also took into account a pressure factor, which changes the cost based off of the operating pressure of the vessel. Ours being so high, upwards of 2,000 psi, obviously increased that price. Next, the exchangers were costed based off of a duty reported by KimCAD and a utility stream decided by the temperature of the operating temperature of that exchanger. Like I mentioned before, some of these exchangers, some of the towers exchangers weren't costed as traditional heat exchanger. They were costed as a furnace because it's unreasonable for a traditional heat exchanger to provide that energy to drive that tower. So those towers were driven, or the energy was provided by a non-reactive fire heater, which was priced based off of a heat usage reported by KimCAD. Next, those towers and the towers were priced as vertical process vessels with a diameter based off of sizing given by KimCAD and a height based off of a theoretical number of trays and a tray efficiency to actually get a real life number of trays for that tower separation. The trays were priced as sieve trays with a diameter the same as the tower and with a number based off of that tray efficiency, like I just mentioned. Next, we'll get into some system optimizations.
So now we'll get into some system optimizations that we've made. First, we'll start off with the most important optimization, and that would be the reactor. The residence time and the temperature of the reactor is most important because this will affect the price of the reactor. And like Clayton mentioned before, this is the largest part of our fixed capital investment cost at 76%. This also affects how much of each coat will be produced and sold, which is our only source of revenue. Looking at the graph, our optimal temperature and residence time at 806 degrees Fahrenheit and 0.41 hours respectively. Our reactor favored smaller residence times due to the large volumetric ratio of hydrogen to VGO in the reactor. The residence times are in skew of each other because we wanted to maintain, if you wanted to maintain a constant volume or volumetric flow for calculating the residence time, it would change after each run. To ensure the accuracy, we would send a pseudo residence time to KimCAD and recalculate the residence time for each run. And next optimization we focused on was the expander. This was the beginning of our separation system. At lower pressures, the system would separate better, but if it's too low, the pressure factor would start to increase for all of our process vessels. That included the towers, the flash drum, and surge tanks. As the pressure drops, this also affected our recycle pump and caused it to have a larger duty to get the pressure back of our operating system. As we increased the pressure, this would have increased the duties and sizes of the separation towers. This would have also increased the pressure factors for all the process vessels mentioned before. So our optimal pressure for the expander was atmospheric pressure of 14.7 psia. Now the final optimization that was on the flash drum's temperature. As the temperature was decreased, there would be a larger duty on the flash drum since it was cooling after the reactor. This would also recycle less hydrogen back into the system. As you increase the temperature, this made a smaller duty on the distillation tower following it by decreasing the required heat from the fired heater. This also increased the amount of gas that would be recycled back into the reactor, which would cause a buildup and cause for a larger reactor residence time. The optimal temperature of the flash drum was 350 degrees Fahrenheit.
My bad.
No problem.
Next, we looked at some process safety concerns and environmental concerns. The majority of the process safety concerns revolve around the potential of a runaway reaction, which can be caused by a few different cases. The first being the recycle hydrogen compressor failing. This would result in a reduced flow of hydrogen back into the reactor, which the hydrogen acts as the quench of the reactor, controlling the temperature, and so there'd be less heat removal. thus increasing the temperature and allowing the reaction to potentially run away. The second case that could produce this would be if one of the catalyst support systems within the reactor were to fail. This would cause channel flow or a misdistribution of the flow, again causing an increased temperature in the reactor, or hot spots, again causing risk of a runaway reaction. So ways to kind of mitigate this would be in robusting our reactor quench, or understanding at what point we might be at risk of a runaway reaction. So in an effort to quantify this, we plotted the duty of the reactor. This is the amount of heat that would need to be removed from the reactor to prevent a runaway, against as well as plotting the potential heat removal that the recycled hydrogen could provide. And from this graph, you can see about around 815 degrees Fahrenheit, we start becoming at risk of a runaway reaction. Next, we kind of get into some environmental concerns. Like I mentioned before, the recycled hydrogen compressor would cause a reduced flow into the reaction. This would cause the reaction to produce more gases, which would need to be flared off, which is an environmental concern. So adding a redundant compressor would not only save us the risk of that causing a runaway reaction, but also a risk of environmental concerns, exposing the environment to VOCs. We'd also want to increase the furnace efficiency, again, reducing the flaring, like I just mentioned, or implementing scrubbers to scrub some of those VOCs out of the stream before they're flared off. And then finally, implementing leak detection. That way, we prevent unknown risk of leaking VOCs into the environment.
And this is our final best case scenario with our utility costs and bare module cost. And at the bottom, you can see the factors going into the NPV costs. And our final best case NPV was negative $30 million and $560,000. And this opens up the floor for any questions.
Reminder, if you have any questions, just send me a message in chat and I can unmute you, or feel free to raise your hand and I can unmute you to ask, or raise your hand in the participant section, I can unmute you. Well, I guess Clayton, also, I guess I had a question on that last slide you had. So with your net present value, your final summary is that this plant would lose, losing money?
Yes, sir. Yes, sir. That is our case. We moved forward with a hydrogen to hydrocarbon feed ratio that was quite high, meaning that we fed a lot of hydrogen into the reaction. This caused our reactor size to, be larger than other cases, which, in turn made our reactor more expensive than probably other.
And I guess that's the question that the first presentation about the price of commodities. And so in yours, it did look like Adam alluded to, they are positively correlated, where if one goes up, it seems like the other ones go up also.
Yes,
so it seems like there is quite a bit of fluctuation there. So there may be some conditions where you'd make a considerable amount of money, and then some conditions where you'd lose a considerable amount of money. But it looks like on what you're saying, essentially on average, it'd lose about 30 million.
Yeah. At least with the way our system, the structure of our system and the parameters that we chose to move forward with.
Yeah, because it would be a set of parameters that would essentially be a break-even point. Like at a certain price, the commodities, you would at least break even, and then above that, you'd make money. You're just saying at that average price, on average, you'd be expecting to lose money.
Yes,
Yeah, should have analyzed it more on each year. But
we move forward with
on
the
average,
that more hydrogen would help our reaction and help us produce more products, and that was not the right assumption. We didn't realize until a little too late to revert and change that ratio.
Yeah, I don't know if you look at every year, but what did strike me is just the fluctuation that where some years it seems like a feast or famine, like a very high price commodity. When there's very high prices, you can sell all the commodities for a high price.
Yeah.
and then all the commodities are low.
Yes, sir. Any other questions? Anybody else?
All right. Well, let's thank our speakers. We can do a visual hand clap here. Okay, we do have a 20-minute break. So the associate dean recommended we keep the recording on, so I'm actually going to keep recording and go straight through. So we'll start up and back again at 2:20, but I'm just letting I'm going to keep recording, so I'll let you unmute yourselves if you want to chat. Just that's a double-edged sword, so remember whatever you say is being recorded, so if you play back the recording, we'll get this 20-minute window of discussion also. So you've been advised.
Been forewarned.
All right. So you can unmute yourself now if you want to, and the next group will start back at 2:20. And is that Anastasia Britton in the house?
Yes, sir.
Oh, it looks like is that Casey Oliver? Two Zoom icons down, or Cassie Oliver? Maybe not. Oh, welcome back, Anastasia. All right. Welcome back to the, I guess, the second part of the senior design presentations. So we have two more groups remaining today. The first one, or the speaking deal, will be Matthew Bullock, Rafael Martinez, and Travis Shaw. Let's see, I see Matthew and Rafael. Travis, are you unmuted?
Yes, sir. Yes, sir. Just unmuted. Thank you.
So Matthew, you can take it away.
All right. Well, this is our hydrocracker unit design. I'm Matthew Bullock.
I'm Travis Shaw.
I'm Rafael Martinez.
And what we're going to talk about today, we're going to go over the process flow diagram, safety, the components that we used, thermodynamics, the kinetics, raw material pricing, equipment pricing, optimization, and the final cost.
So this is our process flow diagram. We have 2 reactors and a total of 5 towers. The second reactor uses a VGO recycle stream. It has 100% recycle. And then it has a gas and naphtha mixture that has to be sent back to the first flash drum for better separation. These are our stream properties. We decided to only record the feed and product streams, and these are the flow rates in pounds per hour. And they check out whenever you do a mass balance on the whole process. So for safety, our main concern was to avoid runaway reactions because we're working at such high pressures and high temperatures. So we decided to add a pressure relief system to the reactor, and we try to keep the temperature constant. And also, in case there is a change in temperature that is not supposed to happen, we have a crash cool reaction mixture to bring the temperature down. Since it is an exothermic reaction, you can go to the next slide. Also, we have pumps, obviously, and we have a VGO pump that feeds the reactor. We decided to add a second pump in case the first one fails. Also, we're working with gases, and in case there is a leak of gas, we have added a furnace to the system, and compressed air system will seal the opening wherever the leak is happening. And since there is corrosion, we are going to avoid it by having an inlet and outlet piping that should be symmetrical.
And so for our component justification, we took each cut fraction and put each component into a distillation column and compounded them, added them into the column. And where it leveled off at is the number of components that we use. So as you can see, the gases leveled off around 4 components. The naphthas leveled off around 5, and kerosene leveled off around 4 again. And then diesel leveled off around 3, and VGO leveled off around 3 as well. And these are the components we used. We based our main base was off the number of carbons that each cut fraction had, or each component had for each cut fraction. We also based it off the boiling point. And then in the next slide, you'll see a assay from BP, I believe. Exxon. And so we decided to go with the paraffins, cycloparaffins, and aromatics for each cut fraction.
So as you said, we referenced the Exxon Thunder Horse assay, and the reason we picked this one, Exxon actually makes multiple assays available. The reason we went with this one is because this rig was located 125 miles southeast of New Orleans, and so we felt like it was a good representation of what kind of crude we would be processing in our unit. And so if you can go back to the previous slide, you can see like for each cut fraction, we obviously, like Matt said, included a paraffin, a cycloparaffin, and a aromatic. And so that's also one thing that you'll see in our kinetics. That was another thing that we had to fit to, basically, is not only to get a certain percentage of naphtha at each data point that we had, but also to within that, get a certain percent of paraffins within that naphtha at each data point. And you can go 2 slides ahead. This just shows the assay. You can see towards the bottom, you can see the paraffins volume percent, naphthenes volume percent, aromatics, and obviously naphthenes and cycloparaffins are the same thing.
So this is just the thermodynamics justification. Since we're working in the vapor phase, we graph the hydrocarbons in gas phase. And this is the graph that we received with the mass fraction and the carbon numbers. You can go to the next one. And since it's hard to tell from that graph, I decided to do a percentage error, and the PSRK had the lowest error with only 10%. So that's what we did our whole model in.
And this is just a reaction schematic by cut fraction. We ended up with like 25 individual reactions, I believe, but they can all be, summed up into kind of this page with, the cut fractions of VGO reacts to diesel, VGO reacts to kerosene, and so on and so forth. And this is just shows the activation energies and frequency factors. Basically, these are the kinetic values that we varied in order to regress our kinetics in ChemCAD. And this is these next couple slides are our kinetic fits. And you see at multiple temperatures, we were able to achieve what we felt like was a pretty good fit. None of them are perfect, but at some points you had to sacrifice some accuracy in order to get a model that would fit at a very, very wide range of temperatures. And you can pause right here. One of the main things that we focused on with regressing this was we wanted to capture a diesel maximum at a certain temperature. And what I mean by that is, so obviously our most valuable components are diesel and kerosene. And so we felt that it was necessary in our kinetics to show a point where the diesel and kerosene start to tail off in order to give us a more, accurate model, or else, if VGO and diesel if diesel and kerosene never showed a maximum, then we felt like when we went to optimize it, it would just tell us to, continuously leave the chemicals in the reactor for as long as we could to get everything to react to VGO and diesel, and that wouldn't be accurate. And this is just continued. So this is a project sensitivity to the component pricing, to the commodity pricing, sorry. And as you can see, and this is something that we expected, this project is very, very, very sensitive to commodity pricing. You can see there's tons of highs and lows. And, obviously intuitively we knew that going in, but I think this kind of shows us really just how sensitive it is to commodity pricing. So we're getting into some of our individual commodity pricing. As you can see, we have a gas prices over time and naphtha. The reason that the naphtha looks a little bit different is because for every other component, we were able to find data on EIA.gov, and they have a feature where you can kind of download it into Excel and you have weekly data points. With the naphtha, we weren't able to find that. And so we ended up finding some data on businessinsider.com. But the issue was it didn't have a feature where you could download their graphs into Excel. And so we had to kind of take the points individually off the data. And so we got enough to where we felt like we were capturing, good trends, ups and downs of the price over time, but we weren't able to get like as many as with gases and kerosene and diesel. And this is just the continuation of that with kerosene and diesel. And kind of like Dr. Shear was saying earlier, if you look at the kerosene and diesel, you can see that they trend very, very, very similarly. And that's something that we would expect, given that all of these commodities kind of come from the same base, which is crude oil. And so pretty much all of them are going to fluctuate with the price of crude oil. And these are just the wholesale prices that we ended up going with based off of a 95% confidence interval on the data that we were able to collect.
And so here's equipment pricing. When we were doing our optimizations for the towers, we found out that the temperatures were varying greatly, and they were causing our NPV, our final NPV, to vary greatly as well. So we decided to put a couple fired heaters in front of each tower, and to get them to level out. And we'll talk more about that in later slides. But here's our fire heater prices and the FCI and the utility cost. And fire heater number 4 was the most expensive fire heater for us. And then going on to the heat exchangers, obviously each column has a condenser and reboiler, and so that's where these come from. And our most expensive heat exchanger was Tower 102, and that was because we are using a refrigerant for our utility costs. And so then on our pumps, we our highest pump cost was our inlet VGO, because that is the highest flow rate we have in our system. And then our reactors, our reactor 101 had the highest FCI cost, around $57 million. And then in our towers, Tower 104 actually had the highest cost, and it is also the tallest tower that we have. So that kind of explains the reason for the highest cost there. And then we also had a flash vessel right after the reactor, which came in at about $11 million FCI.
So now we're going to get into some of our optimizations. This is the first optimization that we started with. Kind of intuitively, we just felt like the reactor would be the component that the value of the project was most sensitive to, and so we felt that optimizing it first was the best way to go. And as you can see, we did generate some curves that look how you would expect. One issue that we did identify was that our data only goes to a space-time of 2 hours, and so we're outside of that range here with our model. And so on one hand, we were able to fit data good within that 2 hour range, and so we feel good about that. But also, this is an issue that given more time, we would have loved to have been able to investigate. Well, we did investigate it. We would have loved to have been able to figure out this issue and solve it. And basically, from our investigation, what we found was the reason that at lower, as you can see, at these lower space times for each temperature, the NPV is obviously very, very low. And what we found from that is that at a lower space time, there's more VGO, or more unconverted VGO, left in the reactor effluent, which is intuitive. The less time it has to react, the more of unconverted feed that you'll have. And so with that in mind, when we went to separate our VGO and diesel in our final tower and recycle that VGO, that was one of our highest cost as well, along with the reactor, was the utility for that tower. Because in order to separate VGO and diesel, that reboiler has to be able to get the streams so hot in order to get it to separate effectively. And so that was kind of the issue that we saw with that. That was causing the lower space times to be so low. And like I said, given more time, we would like to be able to investigate this more and solve the problem. But just due to time constraints and things like that, we kind of weren't able to get as far into that as we would like. And this is just a closer up version of the last slide that focuses on the kind of the optimal range. We went with an optimal point of 779 degrees Fahrenheit, which is, I believe, about 415 degrees Celsius. And that's what we found was our optimal operating point. And one thing I do want to point out here is you can see towards the end of these graphs I mean, these curves kind of on like the right-hand side of each curve, you can see there's a tiny bit of scatter. And so that was one thing that we spent a lot of time investigating, was why on, you know, like on the left-hand side of each curve, it looks like a smooth, good-looking curve. And then on the right-hand side, you start to see some scatter. And so throughout investigating that, that kind of led us into our next optimization. We found that that scatter, well, we found that when we were operating towards the right-hand side of each individual curve, that there was some variation in the inlet feed temperature of that tower that I just discussed, the VGO diesel tower. And so we found that the cause of that scatter was coming from that variation. And so our next kind of thought was, well, if, you know, that tiny variation in the inlet feed temperature of that tower is causing, you know, such a large effect on our NPV to where, you know, there's noticeable scatter, then that should be a variable that we move into optimizing next if it's having that large of an NPV effect. And so as you can see, this is, you know, exactly what we did. We were operating around the 244 degrees Celsius range when we started. And as you can see, just from looking at that, just a tiny bit of variation there would have a, you know, pretty large effect on your net present value. And so what we ended up doing was basically adding an economizer to the inlet feed stream of that tower, more or less. And, you know, obviously we optimized it and found the, you know, optimal feed conditions, I guess. And really it's, I guess intuitively would be the vapor percentage of the feed coming in is what we were really optimizing, but however, we were doing that through manipulating the temperature. And this next slide is just a close-up version of our optimal point. We see an optimal around 360. And so our next thought was, well, if we're manipulating the conditions of the inlet feed, then that might also be manipulating the optimal feed tray location, because we were called from separations, the Q factor, or the inlet, the vapor percentage of the inlet feed kind of changes the optimal feed tray location. And so we decided to couple that with our inlet feed temperature. And we ended up finding that, you know, as you can see, the effect that the feed temperature is having compared to the effect that changing the feed tray location is having, there's a much larger effect on the feed temperature than there is changing the inlet feed tray. And so with that, we thought, well, if our VGO diesel tower, is causing such a huge effect on our NPV because it has to get to such a high temperature, then our gas naphtha tower would likely have a similar effect, given that it has to get to such a low temperature in order to separate. And so that was kind of our next optimization that we did, was adding basically the same thing, an economizer to the inlet feed tray location, and kind of finding the optimal conditions for the gas naphtha tower separator. And so as you can see, we find an optimal around 0 degrees Fahrenheit, or I'm sorry, around 5 degrees Fahrenheit. And this curve doesn't look as normal as some of the other ones. You can see there's like a stark drop off. And the reason for that is at 0 degrees Fahrenheit, we started to have to use a much, much, much colder refrigerant than at temperatures above 0 degrees Fahrenheit. And with that much colder refrigerant, we saw our utilities costs increased rapidly because it's so much more expensive. And so that's kind of why the curve looks the way it does.
And then this is our gas naphtha separator optimization. This is tower 103. And in this optimization, we coupled the number of stages with the feed stage versus the NPV. And as you can see, I believe it is, oops. Oh gosh. I believe it's 21 stages with a feed stage of 14 for is what we found to be our optimal specs. And then in the kerosene recycle optimization, we had the same thing with the number of feed stages in the feed stage versus the NPV. And as you can see, it was 26 stages with a feed stage of around 8.
So our final results were, after implementing all of our, optimizations that we went through, we finished with an NPV of around $52.9 million. And we feel good about that, but we feel, given more time, we could have, I think like every other group would say, we feel, if we had more time, we could have, further increased that net present value.
Are there any questions?
As a reminder, if you have a question, just send me a chat and I can unmute you, or feel free to raise your hand and I can unmute you. All right. If there are no questions, we can give a visual round of applause to our speakers.
Thank you all.
Great job. All right. And give us a minute or two here. We'll switch over to the Zach Call, Travis King, Tyler Libert, and Jack McCullough group.
Mom.
It looks like the 4 of you are unmuted.
Can you hear us?
Yep. So Tyler, you go ahead and take us home.
All right. Good afternoon, everyone. My name's Tyler Libert.
I'm Jack McCullough.
Travis King.
I'm Zachary Call.
And we're going to be presenting to you about our catalytic hydrocracking system that we came up with.
So this is kind of overview of how we're going to do this presentation. We're going to start off with the design of our cracking system and the process flow diagram, the components we selected, and the reaction kinetics that we selected for this process. And then we'll go into our economic analysis, and then that'll be followed by our safety and environmental analysis. And so we're going to start off with design. And this is our overall process flow diagram. You'll see that our reactor is immediately followed by a flash drum, which then goes into 4 towers in series, in which we recycle excess hydrogen and vacuum gas oil to go back into the reactor to react even more. You'll see that we've included temperatures and pressures and a mass balance overall for this system. And these temperatures are set for our base case when we first designed this system, and you'll see that these temperatures will change with our optimizations later on. And so these are the components we selected for our cut fractions of vacuum gas oil, diesel, kerosene, naphtha, and our gases. And we're going to get into how we justified selecting these components and how we have a set number for each cut fraction. And so this is an example justification. We actually would feed a group of components through a distillation tower or a flash drum, and we would remove a component one at a time by keeping that total mass flow constant through that flash drum. And as the reboiler duty on that flash drum changed and went constant, that's when we decided that removing or adding components was no longer necessary, and we had an accurate representation of that cut fraction. And so this is our example from diesel, and you'll see that a number of 5 components was acceptable for the diesel cut fraction.
We also made sure to keep the relative amount of paraffins, aromatics, and cyclic compounds constant as well.
And so for our thermodynamic model, we actually had some issues. We were modeling the hydrogen mole fraction in a vapor stream that was a flash drum immediately after a reactor. And with all these thermodynamic models, we could not find anything conclusive, which was kind of a bummer, but we went ahead and progressed using the UNIFAC model for our system.
For reactions, we originally started out with 80 plus reactions, but we eventually pared it down to 20 by removing redundant ones and ones where during the kinetic optimization we found fit the data best when they're not occurring. So we came up with 16 reactions that are just alkane splitting, and 3 reactions that are cyclic alkanes breaking open, and then 2 that are aromatic hydrogenating. So we used the data from optimizing the vacuum gas oil hydrocracking for our kinetic optimization. We picked this set of literature data because it has the widest range of temperatures and the most points in the residence times. This is what our results for the reaction kinetics. So for all of the temperatures we got to fit the VGO conversion, and the diesel produced pretty well. The kerosene, the naphtha and gas are fine within the residence times given in the literature data, but would expand outwards as you grow larger than it should as we go beyond that. That's not a big problem because our optimal point falls within the ranges where it works, but something to note.
So when we were looking at the material of construction for our system, at the temperature and pressure ranges that we were operating at, it was well within the realm for carbon steel being fine. The situation where you wouldn't want to use carbon steel involved when you had waters, chlorides, and acids at those temperatures and pressures, but our model doesn't account for that. So if you were in industry, you would have to make sure to take into account those waters, chlorides, and acids and use a different material, possibly, depending on how much of that was appearing in your VGO and other streams. You could use a material such as stainless steel in that case. But for our situation, we move forward with carbon steel due to our model not including those impurities.
And just a little side note on that, if this system did include, things such as sours or sulfides produced from the hydrocracker, carbon steel would not at all be suitable for this project. But in the early stages, in the fall or the winter quarter, when this project was first assigned, we decided as a class that they would not be included.
So I'm going to talk a little bit about the equipment and the economic analysis of all the processes. So right here, first off, is our separator optimization. We optimize every separator for not only feed tray, but also the total number of trays. Right there, clear peak on each one at the optimum feed and total tray space. And you can read them on the right there, what exactly those numbers were. I'm going to let Zach talk about this next one, the reactor optimization.
So we figured that the reactor and the resulting products and material costs would be the largest factor in our MPV. So to find the optimal reactor conditions, we just optimized that without including the separators. And we found that the optimal temperature and residence time were 806 degrees Fahrenheit and 1.6 hours. It might be more optimal at higher temperatures, but that would falls outside the bounds of our model.
All right, so here's just a breakdown quick of our separators in our reactor. Those are the actual numbers after taking into account the efficiency, their diameter. We went with sieve trays because they worked out quite a bit cheaper than valve or definitely bubble cap for this type of flow rates. You can see they run in the $1 million to $2 million range. With separator number 3, our diesel separator, or our kerosene separator actually, running the highest, just simply because of the height it had to be to get a 99% 99% purity. That's what we ran with. So, and then our reactor, you can see its volume 73,000 cubic feet, diameter of about 31 feet, and the length, it's a horizontal vessel plug flow reactor, about 94.5 feet, and it costs about $7 million. Here we have vessels, all considered with a hold-up time of 10 minutes on our distillation column. Distillation tower 1, our LPG separator, didn't actually need a hold-up vessel on the top because we're running a partial condenser and sending a vapor stream out of it. And then next to it, those are our different heat exchangers. We went with shell and tube fixed heads because they worked out cheaper than anything else using carbon steel materials. They were perfectly suitable for these DTs. And fired heaters burning natural gas for all of our reboilers and the reactor. Here we have our pumps. Just assumed a DP of 10 PSI, which amounts to about a 100-foot range, pumping fluid down, a nominal 100-foot range. Just assume that to move from one to the next. We're running centrifugal electrical pumps through all of those. And for our VGO recycle and feed, we needed to run positive displacement pumps because the DPs were so incredibly high on those. And then on the H2 compressors, those are recip compressors. We actually had to run an array of 10 because steam methane reformers come off at about 18 bar, what we're looking at, and we needed to pressurize it up to about 2200 PSI. So they were quite expensive. We had to run an array of 10 in parallel. That's all. And then here's our different heat exchangers and the utilities we're using. Chilled water seems suitable for everything we're using. Note that some of them have quite a high duty, so you would have to run the chilled water quite quickly not to boil the water and get into some weird steam and bubble effects. But it was a lot cheaper to price that out than using something with a higher boiling point and a lower specific heat. And then we use natural gas for all of our heaters. Here are all our pumps, what they consume per year, as well as the compressors for the H2. And you can see a large discrepancy there with the H2 compressor array. And then here's just a general overview of our breakdowns. You know, you can see your electricity, heating, cooling, how much raw material we've got after we recycle per year, and how much we're producing per year. And our project worked out to a total NPV of about 2.3 billion.
So next we're going to go over some of the safety, process controls, and environmental portions of this project. So for our safety, we completed a HAZOP analysis for the reactor, all the heat exchangers, both the condensers and reboilers, and the flash drums. And this is an example of one of the HAZOPs. This is the one for our reactor. We took into account deviations in the flow temperature and pressure. And for the exchangers, we looked at those discrepancies in both the utility and process sides. From those HAZOPs, we determined a few things. That for safe operation, we needed redundant pressure and temperature sensors at multiple points in the reactor in all of our distillation columns in the flash drum and on the process and utility sides of our heat exchangers. We also determined that there was some risk for runaway reaction, so we needed emergency cooling and quench for our reactor, emergency pressure release systems for our reactors, towers, and flash drums, our flash drum. We needed an emergency drain to either a chemical sewer or a flare for our reactors, towers, flash drums, and exchangers in case of overpressurization. And we also determined that we needed bypass system for our recycle streams, both the VGO and hydrogen, as well as bypass for our reboilers, so that we could, if our stream was getting too hot, we could go around the reboiler instead of increasing its temperature further. So this is just a short look we're going to go through with the safety precautions for each of the pieces. So as you can see, we have multiple temperature and pressure sensors going to high temperature and pressure alarms for our reactor. In actuality, we would have more than 3. This is just to show it would be along the reactor as it progressed. We would have a high temperature and pressure alarm for our towers and our flash drum, as well as on the utility and process sides of all of our exchangers, whether it's at the beginning of the process of utility or after the exchanger, depends on whether the stream is heating up or cooling down. You naturally want to put the temperature and pressure sensors on the hotter end of the stream, so that you're taking measurements at the point that's most likely to be at risk of rupturing. For the quench, we took the heat released by the reactor as a function of temperature. Basically, this is showing that as temperature increases, it then releases even more energy. So at our optimal conditions, assuming a water temperature increase of 30 degrees, we would need about 250,000 gallons per hour running through the cooling for the reactor. To be safe, the emergency cooling and the quench into the reactor should be able to handle about double that, to make sure that if it does get out of control, we're able to knock it out so that that reaction stops increasing the temperature further. This is just showing all of the points in the reaction that we should have at least one pressure relief system. Naturally, you would want to have multiple redundant ones in these cases, especially in the hotter portions of this process, such as the reactor, flash drum, and the early towers. You may want to have a rupture disc and then a pressure relief valve in series to protect your relief device from hot and possibly corrosive materials from getting to the spring for the release valve. And then for the process control, to maintain steady operation, we wanted to make sure we had temperature and flow control systems for your reactor, a composition control for your distillation towers. So we would actually be measuring the temperature to make sure we're getting the correct cut fraction that's coming off of each tower. Temperature and pressure control systems for the flash drum to make sure that we're getting correct separation for that, and flow control for the recycle to make sure we're having the correct ratio of hydrogen to VGO in a reactor. And this is something somewhat how it would look like for the reactor, for our towers, to make sure that we're getting the correct cut fractions for our tops and bottoms. For our flash drum, and then for the flow system into the reactor. And for our environmental aspects, most of these compounds are carcinogenic and long-lasting and poisonous to humans and animals, as well as a risk of fire with particulates and smoke and or poisonous gases. So overall, we want to make sure that we're very careful if there is a spill and try and prevent it if possible. So the plan would have to be comprehensive, swift, thorough, and proactive to mitigate any damage that is caused by a response, or to stop it from happening stop the leak from happening in the first place. And the specifics of that plan would have to be determined when you are trying to implement this in industry, since we don't know the exact specifics of our plant at the moment. And these are just some of the sources that we used during this project. And does anyone have any questions?
A reminder, you can let me know in chat. If you have a question, I can unmute you, or raise your hand, and in the participant section, I can unmute you. All right, Tyler, there you are. Sloan. So Tyler, Sloan has a question first, and then Mr. Newberry will go with you after Tyler.
Can you guys go back to your PFD so we can see those flows again real quick?
Yes, give me 1 second.
So I've got a couple questions, but I want to focus them on, I think the two most important aspects of refining, which would be, maximizing profits and then safety. Safety being the primary, of course. So your H2 recycle is the highest that I see. So you're bringing in about 150,000 pounds. Oh no, is that 600,000 pounds for VGO feed?
Right, yeah.
What I'm seeing? Okay. I'm just seeing, and I may be reading this a little incorrectly, but where is this flow going? It doesn't seem that you're having a massive production, especially in, diesel. That's what you're aiming for the most in this. It seems to be the smallest. What could you do to adjust this to where you get a higher, product production and, decrease this recycle rate? I'm assuming that's where it's going, but I'm a little curious as to where all your flow is ending up at with the, 600,000 feed flow, and I'm seeing lots of, 1,000 to 1,200 and 500 productions.
Most of the VGO gets recycled. It's a relatively low intake stream here, putting a lot on the pump and our mixer right there. The only way to adjust that would be switching to a different catalyst.
Okay.
Actually get a higher conversion with one pass through.
Okay. So what set this composition? How did you guys come up with that? Because I'm sure as y'all are well aware, you can't just list oil as like C6s or anything like that. It's such a massive range of compounds. How did you guys come up with that? What was the deciding factor of not having any sulfur or nitrogen or anything like that involved in this composition?
Well, that was actually decided by the professor, that we wouldn't have any sour streams like that. Zach could probably explain it better than any of us exactly how he decided what specific components to include to represent the different fractions.
We looked up the boiling point temperature ranges and carbon number ranges and picked compounds that fit into those, and density ranges, and just came up with a composition that fit the overall values of the cut fractions we found.
And we also researched,
Okay.
like, out of those carbon ranges and boiling point ranges, there is also, weight percentages of cyclics, paraffins, and aromatics that made up those cut fractions, and that led us to get a more accurate model for each cut fraction.
Yeah, it's very difficult to do that. Usually we have to backblend to do that in any simulators. I'm actually very impressed with the range that you guys had in there. That's a great job with that. Another thing, Jack, that's a really good point of if you had sours in this, that you can't run carbon steel on it, because you're exactly right. You'd end up with Swiss cheese towers. It wouldn't work whatsoever.
Yeah.
On y'all safety, can we look at that slide real quick? On your controls, I think it was the second one that you had. It showed water on the bottom of the reactor. It said cooling water. And I'm assuming, I think it may be the next one or the one previous to this.
The one about the quench?
So, yeah. Okay, keep going back to those. Go down through those drawings that you had. One of them had an arrow on the bottom left that showed cooling water going into the reactor. I think Tyler was discussing it.
Yeah, I mentioned having a quench in place. Give me
This one right here. Yeah, go back. That was it. That drawing that you had with the control valve and the cooling water pointed.
Yeah, having emergency cooling in a jacket around the reactor and
Okay.
a quench into the reactor in just in emergency case.
So you know, with something like this, it's at such a high operating pressure. You know, other than cooling it, you know, what other, the reactor itself, you know, there's two things specifically that I'm looking for. You know, what other steps do you think that you could take to where you can, you know, eliminate this activity or this reaction that's occurring and minimize this, you know, increase in temperature that's going to, you know, obviously result in our main concern of an increase in pressure and a rupture of this vessel?
There would also be a emergency drainage to a chemical sewer or a flare in case, to get as much of the reacting material out as possible.
You can also put a blow-off valve, obviously, to reduce the pressure very quickly.
There's so some of the controls that they'll use is hydrogen. I mean, when you start having issues like that, you're going to want to cut back on that, because I mean that's the main. I mean that's what's allowing this reaction to occurring. It's one of the main elements. Also, cutting back on your heaters is another really good decision to do on this. I mean, you don't want to hold liquid inside one of these hydrocrackers. You want to keep flushing it through with, you know, this cold oil and everything. It's just a couple things to look forward or look into when working on any projects like this. If y'all end up in one of these industries, I know at all of our 4 refineries, they're actually looking into projects to create a hydrocracker like this. So just in anything y'all do, there needs to be a giant effort into making sure that safety is a massive factor. But that's a very good job on this project, though, guys. I'm rather impressed.
Thank you.
Thank you, sir.
Yeah.
Thanks, Tyler. And Mr. Newberry, I think, has been waiting patiently for. So, Mr. Newberry, I think you should be unmuted now.
Here I am. First of all, I wanted to mention that the hands-on review I was impressed with. Thank y'all for putting that in there. That was good.
Thank you.
I was looking to see that somewhere, and y'all showed it.
You were our inspiration.
And I had a question about the water going into the reactor also. I would think of other ways of trying to get the energy out, stop the reaction, putting water, which is, I understand that you did. You have the emergency cooling and you have a quench that goes into the reactor of water. Is that correct?
Yes, the emergency cooling would be the first action, but if that wasn't able to control it, then the quench would go into the reactor directly.
Yeah, I would just have concern and ask y'all would look at maybe alternate approaches, throwing the water in there at that temperature, the increase in pressure with the water. It just could be a concern there. So,
like throwing water on a grease fire.
So that was just I saw the water going into the reactor on that one diagram and heard it, and I said, I wanted to ask about that. So y'all did a good job of explaining it, and other options to you instead of that. So again, love the HAZOP.
Thank you, Mr. Newberry.
Thank you, sir.
All right. And if there are no other questions, let's give our group a visual round of applause here. Yeah, so thanks to all 5 of our groups. Great job today. It's been a lot of work these past 2 quarters, but very, very impressive presentations from everybody. So that concludes the senior design presentations in this room. So I'm going to stop